Back to our regularly scheduled program. What are we going to talk about? Oh, logistics. There's a class website, grade scope, no Canvas. Don't worry about what Vitaly said. There is no Canvas. Canvas is lame. Everything will be on the web. So assignments. So for today, by the end of today, I'd like you to take the class intake survey. That's the QR code I showed before. That's just to help me and the lab staff understand this class and what their unique, well, not unique, but how you guys are different from other classes so we can adjust content. Homework due, one is due a week from yesterday, and I will have, and labs, you do have lab this week. You don't have to do the pre-lab beforehand. You can do that in lab, but typically you have to do pre-labs before your lab. I'm going to adjust my office hours, so I'm going to make them Monday 3 to 4 so that they better align with homework. So normally homeworks will be due on Monday. That way I'm available. For next week, because we have a holiday on Monday, I won't see you in class. I'll have extra office hours on Tuesday at 11, and these are posted on the lab calendar as well. So if you're just wondering where's my office hours, you can look there. And then you can also see when there's open lab hours for lab help. Any logistics questions? Yep.
Where can we find a slide?
On the website. Scroll down on the lecture page. There's a list of lectures, and then below there's, yeah, you got it. Great. And so again, we do the redacted slides in here, so I don't give away all the information. You guys actually have to think a little bit, and then after the class is over, I'll give you the full slides. So review from last time, easy intro class. Lecture, so we talked about what is embedded system and where is it going, overview of the class, and then we talked about like the high level of system architecture and how it touches GPIOs, and that was to help you get ready for lab. For the remainder of this week, next week, and maybe next 2 weeks, we're going to be really talking about the instruction set, the ISA, memory, and registers, and how all these things work together. So this is sort of a review of 370, or at least a reinterpretation of 370 concepts for the ARM Cortex M0 or M4 line. But then we're also going to be talking about this thing called memory mapped I/O, and that's where you have the core interacts with things outside of the core, which is a subject that you didn't really talk about last time. All right. So today we're going to talk about ARM, instruction sets, or the ISA instruction sets, and then we'll do an indexing problem if we have time. We might not. Any questions so far? Yeah.
What about as far as receiving memory with caching as well when it comes to microcontrollers?
We don't have caching in this world of microcontrollers, so we're a level below that. But we'll get into it. You'll see by the end of this. All right. So let's talk about, it's helpful to understand the microcontrollers you're learning about if you understand the business in which they exist in. So we have ARM. ARM has shipped, they claim, probably more now, 160 billion chips, right? Sold. Wow, that's pretty impressive. They're everywhere. It's interesting to think that they are a fabless semiconductor company. What does anybody know what that means? Fabless semiconductor company. Yeah.
They don't actually make anything.
They don't make anything, they just sell the intellectual property, right? So this is a wild idea. One of the most profitable companies in the semiconductor world doesn't actually sell semiconductors. Why? So what they do sell as a company is they sell architectures, instruction sets, and the intellectual property to glue it all together. So they sell basically the blueprint or the design of the microprocessor and the microcontroller to other companies. So you know some of these other companies. So it's things like STM, which you're using, Cypress, NXP, Apple, Samsung. They're all using this architecture. Now the question for you is, and then of course these companies make variants, right? And the difference between like NXP and STM, they're both selling ARM Cortex M class processors. They're just adding their own special peripherals so they differentiate themselves in the market. They're adding their own special thing to it, but still underneath, if you know how to program them because of what these guys done, then you can switch between these processors pretty easily. Okay. I forgot what I was going to ask. It was going to be a great question. I don't know what it was. It was great. Anyways. Okay. So ARM in general makes 3 different classes of processors. So there's the application class processors. This is tablets, cell phones. These are things that are user-facing in a sense. Then you have the real-time platforms. These are more hardened. They're very much similar to the what they call the microcontroller family or the cost-sensitive family, but they are more robust than and hardened for those applications. There is a wild landscape out there of different types of processors and different architectures, and it's really important that you know what you should be looking up for this class. So here is a bunch of, I got advanced here. So these are chip architectures, and these are instruction sets. And you can see here are the class of microcontrollers that you'll be studying in this class. There are multiple instruction sets that can go with them. For this class, we're specifically looking at the ARM v7M architecture and the Thumb2 instruction set. So just as you're looking online, make sure you're in the right zone. All right, so what is an instruction set? An instruction set architecture. So this is an abstract model of the computer. It defines how software controls the CPU, and it's an agreement between the programmer and the hardware designer that if you program this thing, it will actually function. So the ISA defines like instructions and data types and data storage and addressing schema and data flow control. ARM has multiple instruction sets that you saw. They have a 16-bit, they call them Thumb, and then they call them ARM. I don't know if they actually came up, that's why they said it, but Thumb is smaller than ARM, that's what I remember. But they have these 2 different instruction sets, and for Thumb2, they made what they claim is a hybrid. Well, I mean, it is a hybrid, but they say is optimized, better performance than either individual one, where they have a mix of 16-bit and 32-bit instructions. And they're not all of them, it's a subset, and they say it's highly optimized for both code density, because you have limited amount of storage on these little microcontrollers, and speed. And then different microcontrollers architectures will do different subset of the instructions. So Cortex M0 is the smallest, M1 and M0, and then you have a larger number of instructions, including these for the Cortex M3, M4, and then the floating point variants as well. So we can go through an example here. So architecture defines how the instruction set is being processed on the hardware level. This class focuses on the Cortex M4, which is a variant of M3. Yes, I know that. So, but consider the following example. Even though we're talking about the M4s, this is application class, so this is a slightly different architecture. So the Cortex A8 running this architecture is a 13-core or 13-stage processor application class. The RMV architecture has a 3-stage pipeline. So same type of instructions, it's just the core itself, the hardware, instantiates how it's processed differently, even though it's essentially the same instructions. They both use, or can be used, the Thumb2 instruction set. So here, instructions are different than, are implemented differently on different architectures. Okay, so a little bit of background, yeah.
I just had a question. Are they considered to have the same ISA or no?
No, these 2 are slightly different instruction set architectures. They're both ARM v7, it's just a -M, not M. But they both do the same instructions. So the architecture is different, but the actual instructions is different. All right, so let's go back a little bit and think. So here we have the kind of the evolution here of what ARM has put out over the years, and then they come up with, these were all like 8-bit maybe, and then we got, or 16 bits, and then we got 32, and they have Thumb, which is kind of both, and then they have 32 and 64, and Thumb2, and just Thumb, like they're kind of all over in the instruction set size. So first question is, what technology trends are causing or caused the shift from 16-bit to 32-bit to 64-bit architecture? Why has the industry done this? In this, you could think in the class of desktop processors or even little microcontrollers. And then, given this change, why has ARM focused on making a hybrid 16-bit and 32-bit. So why don't you take 60 seconds, talk amongst yourself, come up with an answer for each one of those.
We don't have any. Address the memory. We're going to get exponentially bigger.
Eventually to figure it out.
What do we think for question 1? Why has the computing industry in general gone from 16-bit to 32-bit to 64-bit? Instruction sets, yeah.
Perform more and larger tasks.
So we can get more performance out of each instruction. Okay. Any other reasons? Yeah.
To be able to address more memory.
Ooh, that's a great one. And that's the one I was thinking of. It's certainly true that you can do more work with a larger instruction, but there was a time, let's say 2005, 2004, where they were limited in the amount of memory that you could have in a desktop computer. Not because they couldn't make computer memory that was more dense, it's just they didn't have enough address space with a 32-bit process instruction set to address all that space. And so they had to switch over to a 64-bit architecture just so they could address more things. And they're limited to about 4 gigabytes or so. What about this? What does this mean for here? Why have we chosen a 16-bit and 32-bit architecture for these small microcontrollers? Yeah.
You might have a lot of devices that actually don't have or need a lot of storage. So
Yep.
sticking with the smaller is better.
So smaller is better. Why not just stay 16? Why not go 8 or 4? Like why go have a mix of 13 or 32 and 16?
You would also need enough bits to decide the instructions going to do.
Okay, so we can't go down to 4. Maybe some researchers made a 4-bit instruction set, but there are 8-bit ones. Why go up to 32?
The long history or legacy of other 32-bits, so you can work with other things too.
No, you were right the first time. You do want to get the advantage of having a larger instruction set so you can get more work done. But you don't also want to have such a large instruction set that you can't fit it all in memory. So they're like, we don't have to address this huge, very large, over 4 gigabyte memory space, but we want to have the advantage of 32 bits instructions to get more work done when we want, and we want the code size of 16. So this is the trade-off that they're trying to make. Okay. All right, so let's talk a little bit about the ISA in terms of memory, registers, and data width. So we remember this complicated diagram from before. For the purposes of this lecture, and oh yeah, all the bus widths are 32 bits. We're just going to consider the core talking to unified memory. They don't have any difference between flash and SRAM. We're just going to talk about unified memory. And that's how ARM, it's actually an important point. This is how ARM thinks about the world. So ARM doesn't know, let's go back to this picture here. Now I remember my question too. Why don't these folks just make their own processors? It would be easy. You don't have to pay any licensing fees to ARM. Yeah. Oh, you gotta be real loud.
Nobody would write software for them?
Well, it's okay. But at least, especially at the lower end stuff, maybe not. Yeah, I mean, you can always hire people to program it and teach them how to do it. Any other reasons?
It's stupid to reinvent the wheel.
Okay, that's partly it, right? Now imagine that, and you're not wrong about the programming part, but imagine every manufacturer has to make their own really good processor, and it's hard. There's lots of little error conditions, there's lots of things to keep track of. Now you have to make tool change from it, and you do have to have people that are trained on it. It's nice if you buy this and now you have somebody else responsible for all those errors that can occur in keeping track of the processor architecture. And you do have a workforce that's flexible to go through it. It's just that now these guys don't know, or ARM doesn't know how NXP is going to specialize their chip. ARM doesn't want to make an ISA specifically for NXP. They have to make one that everybody's going to use. And let's see. And so when we come back to this here, we're going to talk about unified, this is a unified memory. This is from ARM's point of view. What ARM does is they just say, okay, here's some address space. So here we have addresses going up, and they're just going to say code exists between this address and this address. They're going to say SRAM's here, peripherals here, external memory, device, and this other things. They're not saying, they're saying this is the maximum it can be. They're not saying exactly what it's going to be. It's up to the manufacturers to go through and decide, okay, well, I only need code space that's a certain size. I don't want to instantiate whatever this is, a half a gig of code of memory on my device. It would be too expensive. I'm just going to instantiate a little bit. But ARM is saying, well, your code has to start here, your SRAM has to start here, your peripherals have to start here, so that their ISAs work and their tool sets work. So here there are, 4 gigabytes worth of memory described here. That's lots of memory locations. Sorry, there's 4 gigs of memory locations. It's all in unified memory structure, but this is independent of the implementation. So memory regions are predefined but for operability, but there's no guarantee this is actually going to be the case. So if we look for your specific microcontroller you're using in the lab, they have a lot of these reserved spaces. You'll see this in datasheet. Reserved doesn't mean that it's there. Reserved just means that they're reserving it for maybe in a future architecture they're going to go implement something here, or maybe in a different design. It's just not implemented. These addresses and this memory does not actually exist. They're just saying, here's boot, here's flash at this address, here's SRAM starting here, and up and up and up. Yeah?
Can we use those addresses? Or
They don't exist.
you just can't write them?
Yeah, there's literally no storage elements there, and your compiler should throw an error on you, because your compiler should know what chip you're using. So there's just nothing there for you to do. It's just they just didn't implement it. But instead of having ARM keep track of everybody's little implementation and making it as small as possible, they just say, here's the regions you can operate in. Yeah, basically said all that. Yeah. Okay. So here we have, let's see, SRAM, okay. So here's unified memory. Why? So the ISA, like I said, ISA treats SRAM and flash as a unified block of memory. Why would a microcontroller want both types? What's the advantages and disadvantages? Yeah.
SRAM is fast, but it takes up more area. So you want to have a little bit of it when speed matters.
Yeah.
But when you want more storage, you can use flash memory.
More storage for flash memory. See, I think isn't SRAM denser than flash? I think so. It's definitely faster than flash. What's the special thing for flash? Why do we need flash on there? Yeah.
Doesn't erase when you cut power.
Yeah. So he said it's non-volatile. He didn't say that. He said it doesn't erase when it, power gets taken off. We use the term non-volatile. It's just nice that when you unplug your device, you would like to have some amount of memory that is persistent. So when it boots up, you boot out of flash, and then you boot your program into SRAM, and you work in SRAM. And SRAM is very fast. It doesn't have that speed penalty as flash. Okay, so how are we going to organize our memory addresses in this space? So each memory location has a 32-bit address. However, each memory location can store a byte of data. Okay? However, that's not probably how we really think, or how I, thinking about a 32-bit system, would think about storing information. It's not that I store a byte every time. I can store words or half words. So the alternate way to think about this is, so here we have ascending order. And so now I can say this address can store a word. Now the difference here is I start at AC, and here's AD and AE and AF. We're just not showing it in this pictogram. And then here we're going to increment by 4. So most of your operations that you'll do is actually 32-bit operations. You're going, because your buses are that wide, your whole system's set up for that, you're just going to be storing and loading 32-bit words. You just have to make sure you're doing it on the index of 4 so that you're getting the data out. However, you have the opportunity, if you should do so, is to store bytes and half words. Does that make sense? Part of this is you need to know your indiness. Unless otherwise stated, you can assume that we're a little Indian here. Most of the problems that were inconsistent between lab and lecture, or with even in lab or lecture, is which way our addresses are increasing. Are they increasing up or increasing down? Yeah.
I have a question about, like, a couple slides back, the memory organization. Why does ARM make any distinction between all the different memory sections? Because, like, it's just doing like loads and stores on like certain addresses. Why do they say like only your code can exist here and not exist over here?
Sure. Because, that's a great question. Let's look here. So some of these things have specific functions. So we're going to learn later that part of what we call memory mapped I/O is that your peripherals like GPIO pins and timers are actually just memory addresses. And the way the core interfaces with them is just by pushing data in and out of memory addresses. Now, it happens to be that those memory addresses will cause things to happen like GPIO pins to go high. The core doesn't know that. You as the programmer knows that. So back to your question is, they could make it go anywhere, but a lot of these have very specific functions. Like SRAM is a certain type of memory. And the flash would be is another designation that's not on here, but flash would be a different type of memory, and they've allocated that as well. Does that make sense?
So like would the Cortex execute like a different instruction if it's going to try and be like addressing something that's going to be like SRAM versus memory mapped I/O versus something else, or is it all just loads and stores?
From a core's point of view, it's all just loads and stores. It makes things easy for ARM, right? Their core processor just does loads and stores. And then the documentation, right, or the IDE interprets that as, okay, this GPIO pin is going to go high or low. Like, you have to know that marrying to this memory address means something else than just storing data.
So then, in theory, if I was like an STM like board manufacturer, could I put like my memory mapped I/O in the SRAM section?
So say you're STM, you could probably do it. I think ARM would probably say, well, you're violating our terms of service. We're not going to indemnify any horrible decisions you've made, right? And then when you hire the new junior programmers that took 373, they're going to be like, oh, no, I'm just going to put my data here. And all of a sudden, their GPIO goes crazy. And then, so that's bad. And then your IDE tools would have to be changed for each particular processor. So there's no inherent reason it can't be done. It's just not convenient.
It's just like a convention.
All right, those are great questions. What questions? Yes?
Why would they fragment memory and add a bunch of reserved sections instead of just having one massive one?
So different processors, even in the STM line, have different amounts of memory, of SRAM, let's say. So you can buy little processors, they're cheaper, because really it's all about die area, right? So if I have left memory on there, my die can be smaller. And now, so let's see, it's not a good example here. Let's go back up here. So say this is SRAM, right? I just want to go and use a little bit less, but I don't want to have to change my tool sets and all my instruction sets and everything for different amounts of memory. So they just allocate it and they just don't use it. Does that make sense? And when I mean allocate, like on a piece of paper they do, they don't actually put hardware in there. I feel like I didn't answer any of your questions.
Kind of.
Oh, ask it again?
So why don't they just have one entire reserve section instead of like...
So when you go to another processor that has more memory, then you'd have to move everything else up, right? And now it's just more keeping track of all the little details. And like my peripherals would start at different stop and start points. And so it's just easier from a bookkeeping point of view to say, my timers always start at this memory address, regardless of how much SRAM I have below it. So there's no reason you can't do it, it's just not convenient, and that's not how it's done. right? And so like code would be, here's like flash, here's SRAM. If you move your code, made your flash larger, which would be more convenient, you don't want to have to move your SRAM around and just be incompatible with other things. Also, if you go back to here, there's architectural choices underneath, right? There's an entire different data bus for SRAM than there's instruction, right? And we're not going to teach you all the nitty-gritties of this processor, but there's an instruction bus specifically, and there's a data bus, and you don't want to have to, and then your core is optimized to fetch instructions, so you don't want to have to mix these two up, and now your core is doing weird things, right? You don't want to take data and try and be passing it to your instruction fetch and decoder logic. Okay. What other questions? These are good questions. Yes?
Can you go to the little big ending slide again?
Yeah.
So like,
there's a chair over here, by the way.
well, before I move, so, well, actually, I don't know if it's on this slide, but at least like when we were in the lab, one thing I noticed is that when it was like big endian, like all the hex letters were in order, but then when it switched to little endian, it's like you move 2 digits of hex at a time and rearranged.
Yeah.
So why is it like that? Because that just even made it confusing.
So I do have a slide later on it, and it's because we have not, as a species, come up with a perfect convention. And how you ask in lab to display memory addresses, whether it's word addressable or byte addressable, changes the order of what you're seeing. So it is something to keep track of, and it's horrible. All right, any other good questions? Even bad questions? I can answer those too. Okay. Let's see, where were we? That's not interesting. I mean, it is interesting, but we're behind now. Okay, so far we've talked, nope, don't like that one. All this, I don't know why it's frozen. All this, okay. All this slide was just showing you is that like different types of data are stored in different locations. I guess the things to remember about the slide is the stack grows down. And the stack is for things that are dynamically allocated, or like not dynamically, but things that are run at runtime. There's constants which could be put on the heap. We don't generally use the heap in this class. Like you can use it, but we just don't teach it. It's just an extra piece of complication that's not that necessary. But we'll do a lot of stack work, and you just have to remember the stack grows down. Okay, so what you should have learned so far. Did I talk about registers? Should have. Here we go. So just like in 373, your core has a set of registers. These are 32 bits wide. You have general purpose registers like R0 through R9 or so. And you have some, or 13, you have some special purpose registers. You have a stack pointer, a link register, and a program counter. There's other special registers we'll talk about later. These are things that keep track of like your program status. We'll talk about interrupts and faults and control logic. You don't have to worry about them now. There are 2 different modes your processors could be in. We don't really address that. It only comes up with interrupts. So there are shadow registers that you may see, but those are privileged and non-privileged mode. It's not that big a deal right now. So anyways, you have 13 registers that can be used as a scratch space. Stack pointer, link register, and program counter. All right. So far, we've talked about how memory is organized. Memory can hold instructions, memory can hold data, and we've talked about the register organization. So we're going to jump ahead to, yep.
Is this a typo, the memory address for data 4 and data 3?
Data 4 and 3.
They're the same.
Oh, yeah, that's a good typo. One day I'm going to have good slides. I need more people like you pointing out where my slides got off. Let's see.
He's waiting.
32. Okay. Where are we going? Oh, talk about instructions. Okay, let's go ahead. So there's different types, arithmetic, moves, flow control, branching. We'll give you an overview of them. You're not your job is not to remember every instruction. Good God, that would be horrible. We'll give you reference sheets for exams that you can look at. Yeah.
On the previous register slide, what's the difference between the low registers and the high registers?
Ooh, that's going to be a tricky question for later. I don't want to give that away yet. It is somewhat valuable to learn how instructions are encoded, not because I think your ability to transfer between, whatever, this code or assembly and binary is important, but if you understand how it's done, then you understand the ramifications of why the processor was made the way it is. So you will see things like, if you look through the data sheet, so this is a screenshot from the data sheet, sorry, you have many data sheets. This is from the architecture reference manual. You can see the encoding for a instruction. So I'll just go through it. You can say here we have a move. This is a move S, which means you're going to set some status registers. That is denoted, where's this, the S bit? S here. And then what does it say? It says I'm going to do an immediate 10. I'm going to move that into register R0. So that you can go through and kind of figure out how that encoding works. So here we have the destination register, and here we have bits for an immediate. So now you can go through and do the task of figuring out what that binary encoding is. So here you have the operand, you have some other bits, then you have the destination, which is 0, 0, and then you have 10 in binary. Okay? Now, ARM goes through and says, well, if this is only a 16-bit encoding, and I want to encode this next value, yeah, what happened? Yeah. So here I'm going to go to register 1, and I'm going to move in a 0, so I'm going to make an immediate into that value. I can store that in the same memory address, right? So remember, these are going by 4. This is a world that you can store in bytes, half words, and words. And so to save space, you could have made this all zeros, could have been fine. But to save space, we're going to put 2 instructions in one 32-bit memory location. How do you feel about that? I'm sure I have not been clear yet. Somebody has a question. Yeah.
What are those extra 2 bits between the instruction and the register?
These? It's whatever those smart architects decided. They decided they want 2 zeros. I do whatever they say. I don't have any choices. Yeah.
How come we only have 3 bits?
You got to speak so loud.
How come we only have 3 bits to index the register if we have 16 registers?
Oh, so you're starting to see. I put the diagram up here, and you're starting to see all the flaws. We're going to get to them. We're going to get to the good questions in a second. Okay? This is a 3-stage, so you got a program counter that index memory, and you still have to do the fetch, decode, and execute cycles. Yeah. This is a 3-stage pipeline. And if you happen to get a memory location that has 2 instructions, you're just going to stall for one while you're waiting for that next. You're going to decode this one early and have it ready for the next one. So it's not that you only pull out 16 bits. It's that you pull out all 32, check to see what's going, what types of instructions they are, and then you go and execute them in your pipeline. So the question for you is, when the core does a fetch for the next instruction, how does it know if it's one 32-bit instruction or 2 16-bit instructions? So why don't you take 30 seconds, brainstorm, how did these architects figure this out? Because they're trying to save space, but sometimes they want the expressivity of a 32-bit instruction, and when you're pulling data out of memory, you just don't know what it is. It's not defined. So how are they going to do this?
Maybe there's some. I'm like, okay, the gears are coming back, like they're turning
I'm
again.
like, okay, this assumes everything for the 370.
Yeah.
All right, what do we think? What is some way you could accomplish this?
There's probably some bits set aside that like it's like a flag or an indicator that says if it's one instruction or two instructions.
Where are these bits held?
It could be those two mystery bits we had earlier,
Okay. Yeah.
or it could be the register identifier themselves.
Well, you got enough of the answer there. So, and you wouldn't know this unless you took this class, but they're going to allocate certain operands here, or certain codes that indicate that this is a 16-bit or a 32-bit. So they're just going to have dedicated bits for that task that are part of the instruction. And so the 32 bits instruction comes out of memory, goes into the decoder, is looking to see, okay, is it one of these three patterns? If it is, it's this type of instruction. If it's not, it's the other type of instruction. That's all they're doing. Okay? Now, let's see. There's lots of ways to encode instructions. So this is an move and immediate. So this is a way to generate a constant or a value. And there's lots of different ways to do this. So we can kind of guess which. Let's take a guess here. So here we have, this is a 16-bit instruction, and this is a 32-bit encoding. If you wanted to get the smallest, what type of encoding would you use for move S R3 pound 5? Sure.
Well, I had a question for
Oh, sure. What's up?
for the three-stage pipeline.
Yeah.
Is that a in order or out of order small?
I don't know. I'd have to look it up. It's probably in order. No. Yep.
So for 16-bit instruction, are those two mystery bits, are they always 0?
Yeah, they're just defining that this is that first 5 bits, and I don't know why. I don't know why they put the space there, right? They could have, or a little slash there. They should have just made it all 5, and it would have been easy for us to understand. But for this one, what encoding could you use? Why take, yeah?
16-bit?
You could use a 16-bit. I mean, you could do the same thing with a 32-bit. It's not like it's impossible, but you could use T1 encoding. So I can get the binary value of this into these 8 binary values, and I can set the destination register as R3, right? So I have enough bits for that. How about R915? I see one person telling me it's encoding too. Fantastic. Why?
Is it because we can't index as much with the G bits?
Yep. So here, I cannot get the binary value of 9 into 3 bits. Therefore, I'm forced to go over here where I have 4 bits. Okay? So that means this instruction, right, cannot access those upper registers. How about this instruction? Which encoding would you use for this one? Hold up your hands. Let's see. 1, I got some 2s. I think the 2s win, and this side of the class is beating your pants off. A lot of people over here raise your hand. You are all terrified of me. All right. Okay, the hint is, what is this in binary? And can you fit it in here? Right? And so it's going to be encoding type 2, longer instruction. So even though you can get to it with 3 bits for the destination register, you can't make an immediate that large. All right, so, oh yeah, go ahead.
Yeah, I have a question. So M8 is still only like 8 that's long on the 32.
They trick you. So once you get zen with the instructions and your brain gets real foggy and you kind of finally see through the mist, what they're trying to show you here is that you can concatenate immediate 8 and immediate 3, and they kind of show this here. Oh, and you get an immediate 1 here. So here they're showing you the concatenation. Why did they choose to spread it out throughout the instruction? I don't know. We're living in their world. So that's here you get. This is where you get enough bits to do that. Yeah. We'll talk about what move S is later. This is just a move operation, and we're going to set some status registers. Yes?
Just for my own understanding.
Yep.
416 in binary is being split up between immediate 8 and immediate 3 to have enough bits to represent it.
Yep. And then it's telling you here, here's how we're going to concatenate these. Right? Because it's not, I mean, it logically makes sense to us that this is like the most significant, and then this one, and then that one. But I don't know, they could do crazy things. So if they switch it around, you can look in here and see what the concatenation structure is. Yeah.
So the concatenation does go from left to right. So for the 416, immediate 3, the last bit of immediate 3 would carry the 1 for 416. And then the next 8 bits would be in
So I would say, what are we? Yeah, zeros. So here's the zeros from here. If we're going backwards and we're building up, and then 0, what is that? Yeah. So you just, I think the trick really is to watch this structure. So this here tells you the order of the concatenation. If they took the I and put it in between, then they would have mixed it up. So that how it's laid out here is not totally telling you what the order of the bits is. I don't think I've ever seen it the other way, but they're telling, they always add the concatenation instructions. Yeah.
So if it had, so if it did a 16-bit instruction, right, and right after that it needed to do a 32-bit instruction,
yeah.
Would it fill in a 16-bit instruction and did nothing, or would it just convert the 16-bit to a 32-bit instruction?
It will. So your compiler will always try to get you in 16-bit instructions if the encoding can be done that way. But if, from a layout point of view, you're putting in instructions, if there's a gap, then it's just a gap. I think they just put all zeros in and you're done. Yep.
So in that hint, there's 12 bits, but you only have 11 bits in there?
Is that true? Well, that's a bad hint. Let's see. 8, 9, 10, 11, 12. Wait. 8, 9, 10, 11, 12. I have the ith bit.
Oh, I didn't see that. Okay.
Yep.
Wait, is all zeros a no-op? Or is it just like, it's going to be more and you can fetch that?
It wouldn't be a no-op. I think it would just be an ignore. And so I believe it's all zeros. We'd have to go look up at, in the architecture what's actually stored there. So I don't actually remember exactly. I think it's all zeros. There are no-ops. That is an instruction that's separate. Yep.
So does the system half works? Like now it goes 0 to 15, 0 to 15 versus 0 to 31. So
do you mean here, the indexing?
Yeah, but the difference between T1 and T2 is
yep.
set up so you can easily switch between 16 and 32 bits based on how large an immediate is.
Yeah. I mean, so your compiler is going to look at your assembly instruction and say, okay, now I need to turn it into binary, and it will pick the most appropriate instruction size. And then this is just showing us this is just easy for those humans to read. Does that answer your question?
So basically, if you can fit within a smaller size, it'll pick the smaller size and only go up when it needs to.
Yeah. Just save space. That's all it's trying to do. Any other questions? Okay. So you guys kind of got to the answer pretty fast, but why does the ISA make a distinction between low and high registers, and how does this instruction size, 32-bit versus 16-bit, impact how we use high and low registers? So take 30 seconds, talk amongst yourselves, come back with an answer.
I want you to use T2.
If you're doing I mean, this is stuff that is really. Monday there was 300. Yeah, no. Yeah, that was my thing. I was like,
all right, what do we think? How about over here? Somebody over here. Yes.
Yep. But if you go high, you have to use it.
Yep. And so this is where the architectural choice to allow for small code density, right? We live in a world where memory is expensive, in terms of physical space costs money, different than your desktop computers. You have as much memory as you possibly want, it seems. They said, okay, I am going to make 16-bit instructions, but the penalty for that is I can only really access the lower registers. That's the only space I get to use with those small instructions. But if I do want to go to these higher registers, well, I do have that option of a 32-bit instruction. So you kind of get the flexibility of both worlds. Now, of course, ARM, you see, those awesome graphs that they always show, like Apple and all these, where you have no axes and you always beat, right? So they're saying they're better. I've seen this graph. They're better than 16 and 32 in terms of performance and code size. They're like really. I don't know how you can be better than both, but they're better than a linear combination even. So okay. Any questions here? Yeah.
Does this mean that it prioritizes using the low registers so you could put more instructions in?
Yeah. So your compiler has to be smart about this, right? So it will certainly optimize functions, and it will certainly optimize your code to use the lower registers, especially if it's repeating tasks, right? So it will store up here when they have to, but it's not optimal. Yeah.
So 16-bit will not be able to access the 13 to 15?
It typically won't be able to get 8 through 15.
Oh.
I mean, certainly we could construct a 16-bit address, 16-bit instruction such that you could encode enough information to get up here, but then you wouldn't have enough, it wouldn't be expressive enough in the rest of the command, right? So they just basically said lower registers are for 16-bit instructions. Those are what you can get to. Yes?
Is there an instruction by any chance in the ISA where you can make the 16-bit instructions address the high registers and set the most significant bit?
I bet a very clever student can look through the 1,000-page instruction ISA and find one. I'm just pointing out that is not the intent, and they specifically make a differentiation that 16-bit are optimized for low registers and 32 bits are for high registers. Yeah.
So if we're intermediate of larger than 8 bits, say 11, would it mean that the microprocessor will prioritize a higher register? It would be 32 bits in it.
So I think what you said is if you need to make a large enough immediate, then if it can't fit within if we go back here, I can't get. It wouldn't fit in the. A T, so yeah, a large immediate won't fit in a T1 instruction.
It's using higher registers.
Oh no, it can be any register here. It will always prioritize if your assembly instruction can fit within a T1 instruction, it will do it, right? It will try to get it there. Yes, maybe your assembler or your compiler is smart enough to say, only put this up somewhere else, but then you still have to manipulate it, right? So I don't think any reason why your compiler would choose large numbers or prioritize for higher registers. I don't think that's what's going to happen. Yeah.
For T2, there's 12 bits that they're constant, 1 or 0. Do they really have to have those?
These?
Do they have that many instructions that they have to choose between them?
I don't know. Certainly here, this is the instruction encoding, tells you what instruction it is. I don't know exactly what these things function as. As users of the ISA, we don't get a lot of insight into their choices that they've made. I'm really trying to get you to think about why we're using 16-bit, 32 bits, and how those decisions are made. And it's really made on destination size and bit size. Yeah.
Because most of the time it's going to be, regardless if it's if it's a number that you want to determine at runtime, it would always just be a 32-bit instruction. But
no, that's a good point. Probably, yeah. All right, let's go on. So we're going to quickly overview some instructions. Again, you're not supposed to memorize instructions. That's why I have pieces of paper. But it's good. You are expected to know basic instructions like an add, a subtract, a move, a load. So we're going to go over some of those. And then specifically, we're going to get to the point where we can talk about how these instructions impact working with external memory, or memory outside the core, which is still on your device. All right. So if you really got excited, these are kind of the instructions that I would want you to look at. A lot of these are just not that important. And again, you'll see on the handouts that we give you which ones we think could possibly be useful. Okay, so there's lots of common arithmetic instructions. You could look at them. We have add, carry, subtract, all that good stuff. But there's a special set of modifiers you can put on these, and you can add this S at the back. And that S tells the compiler or the assembler that you want to set the status register flags. So status registers here are the outputs of your ALU, right? So you have different like 0, negative, carry, overflow. You have these status rads, and now you can tell that I want the result of this instruction to update those values so that another instruction can figure out, can operate based on those values. So this is part of the application program status register. It says reserved here. In this case, I happen to know what's there because they have this 32-bit string controls also the interrupts and a bunch of other things, and this is a sub-register in a super register that's just called the program status register, I think. But anyways, for the purpose of this slide, you're just looking at those particular bits here to say what the status of your ALU is. And so we can go through an example. Here we want to add two 64-bit numbers, and there's going to be a carry through. So just as a memory or a walkthrough, so here we have two ways to make an immediate. This is a move immediate but an invert. So we're just going to take the value here and invert it. So these are fast ways to get constants into your program. So here we're going to set up the values of FFFF, 2, 1, and 4 in these registers 0, 1, 2, 3, and 4. And then when we do the add operation here, where we're adding, let's see, those two bits, C and B and A, then we need to figure out if there was a carry. If there's a carry, then, it will update those flags, and then add carry will check that flag, add these two things together, and add that flag there. So just a way to modify status registers. There's explicit nomenclature and assembly for doing that. Okay. There's a bunch of bitwise operators. I'll tell you a few that are particularly useful to remember. So bitwise logical OR. So here you're going to OR two things together. I want to set these bits to 1. This one happens to already be 1. That's fine. This one's 0. So now we're going to set it to 1. Why would you ever want to use a bitwise operation? Why would this be useful? Yeah.
Preserve or modify certain bits.
Yeah, and particularly for embedded systems, you have an output LED array. You don't know what those other people have done with it. Some other parts of code is running. And so you just want to turn on your LED, and you don't want to take the time to load in the registers that control all the LEDs, or it manually and put it back down. So here you can just bitwise OR it with whatever's there and put it into your register. All right, other ones that are particularly useful is bit clear. This is just good for manipulating registers. So here is just a way to go and zero out all those registers. So should be a bit of a review from 370. This is a great way to control and manipulate flags for lab. Okay, we talked about move and move invert or not. We have some other specific, you can move to a specific register in different ways. But let's look at two more valuable concepts. So one of the problems here is I cannot make a 32-bit constant with just a move instruction. right? It's just not possible because I have a 32-bit instruction. I can't put a 32-bit constant in that. And so the architects have said, okay, well, I will provide a method to help you do that. So here they have move wide and move top. And so move wide here says, okay, this is the value that's in, say, existing value, and I want to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8 into this register. First, you can set these values here. You can do this, move wide, we'll put it in here, and it will clear out all zeros up above. Okay? Then you can do move top, and move top will preserve, right? It's not going to go and erase these values. It's going to preserve the lower bits. So it's a special operation that preserves these bits when you're writing that in. So now with 2 operations, you can get a 32-bit value in this register. It doesn't work symmetrically. It's not, you can't go say do move top first. So move top would go and move in 876 into the top part of that register, leaving there whatever was there before. And here I'm just showing that was A. And then if you did move wide will go and clear out the 876 you put in there by putting all zeros. So there's an order of operations necessary to instantiate a 32-bit value in a register. They've given you special instructions that will be helpful later. Yeah?
How is there a space in the instruction for a 16-bit immediate?
Sorry?
How's there space in instruction for a 16-bit immediate?
How's there space in the instruction? There is special instructions that give you enough space for it. I showed you one that was the T2 encoding. There's like T3 and T4 encodings as well. It's a good question. A hole in my presentation. What else? Okay. Now we'll get on to things that are specific, you probably haven't seen before, or specific for this particular class. So there's operations like load and store. So load is specifically a class, load and stores are instructions that allowed you to talk to external memory. You're not going to use move. Move is for only manipulating registers inside the core. We're talking about load and storing data in and out of memory. And here you have, this is the address. This is a register. R1 holds the address of the memory you're trying to get to. And they're showing you that this is, that little bracket here helps me remember that that is talking about memory, while this is the value of the data. So here we're going to load the data that's stored in memory at our address R1 and place it into register R3. I think I just said that. And again, there's different encodings here so that you can get to different memory sizes and different register sizes. There are different store operations. So you have kind of standard load and stores for 32-bit, but you can also do half word, you can do signed, you can do unsigned, or unsigned and signed. You can also do 8-bit operations, signed and unsigned. Okay. So an example is here. So here we have 32-bit operations, load, sign, let's see, load register, sign, extend half word tells you that you can go, when you go and place it in the register, it will, or take it out of memory, it'll do sign extension if that's what you've told it to do. So that's nice. If you happen to already know there's a signed number in there, then you can pull it out, and it will, it's convenient in the sense that when it lands in your register, it'll all be signed extend. My question to you is, why is store register sign extend half word not useful or valid instruction? Why are they, didn't make it symmetrical? If we go back to this slide, you see that we have this, but we don't even have a version here. Why aren't they making a signed word store operation? Take some time to chat with each other.
For the story.
Just like
Because it can only read and write so many bits.
Why does that?
So if you have like FFF,
All right, what do we think? Why is there no store half-word sign extension, sign extended? Loud, you gotta be loud.
Yes, we don't have a signed version of storing a half word because if we're storing a half word, we only want to touch the 2 bytes that we actually are storing into. Like, there's nowhere to sign extend.
You're just saying memory, right? Because by definition I'm doing a half word, I make no claims about these other things. That would have to be a whole different. That's like a 32-bit instruction, and so it's not even a valid question. That's fine. It's a good reason. Is there another reason? Yep.
You would like, I don't know, like waste data even though you can just load sign extended anyways. So
yeah.
Not much of it.
Also, there's memory is not typed. It's just raw bits in this architecture. So it's you as the programmer and the compiler that has to keep track of, is this data signed? The memory is not instantiating or retaining that information anyway. So it doesn't really matter what you put it down as, because there's no space to, because you did half word, there's no space to do sign extension here, and it's just raw bits. That's how memory operates. All right, so somebody asked this, a word of caution about your IDEs. So depending how you view your IDE, there is going to be different representations. You have to remember, is your memory addressing going down or up? This is showing byte-wise, this is showing half-word-wise, and this is showing word-wise. And so it kind of puts it on you to be able to interpret your data. Like this looks completely different than this, but it's exactly the same. Okay. So we talked about load and stores as this way of, you have an address in your register and you want to go to that location of memory and pull out data and put it in another register. There's other load and store manipulations that can be done. So there's 3 of them. So there's offset. So say you have a base register and you know that there's peripheral things that need to be done relative to this base register. So you can put an offset. So you're going to load off based off an offset. Then you can also update your register, your address register, by saying stuff like, this is an immediate. This means change the value in the register by this offset before you go and get in data. And this is after you go get the data, change the offset. So we'll walk through some examples to make sure that's clear, because I guarantee it was not. All right, so here's just normal load operation. We have the address stored in R0, okay? And we're going to go out to memory here. So this is the address. We're going to go to this memory location, and we're going to grab this value, and we're going to load it into R1. Now you notice that here I'm being tricky to you, right? So here I'm incrementing by 1, which means these are all byte addressable, okay? If I had incremented by 4, then it's still byte addressable, but this would represent an entire word. Here it represents a byte. And I'll try to be consistent by putting the extra zeros there if it is a word addressing scheme. Okay, so here I'm going to go to this address. I'm going to take this value. I'm going to put it here. What's the value going to be here?
1, 2.
Yeah.
0.00078.
Ooh. Fine. It's actually going to go through, because it's a word size operation, it's going to go here, it's going to grab the entire word's worth of data, okay, and put it over there. All right, so now we're going to look at offset addressing. So here, there's an extra #4 added here, and we're going to say for that address that's stored in R0, let's add 4 to it. So we're going to go out on the fly. is you don't have to do calculations here. It's not an ALU operation per se that takes extra cycles. It's within one cycle. You're going to go here. You're going to add 4 on the fly, which increments your index by 1 word. You're going to grab that value, and then you're going to pull it back into R1. Okay? We can go for pre-indexing. So here, the same thing as before, there's a bang at the end, and that just means we're going to do it right now. So here, before we do the load operation, we're actually going to change the value in R0. Again, in one cycle. There's not an ALU operation where you have to add this together, using instructions, that is. Here, you're going to add 4 to it. Then you're going to go out and go to 8004, grab a word's worth of data because we used load as a 32-bit instruction, and we're going to bring back that data. And finally, post-indexing, we're going to go to that value. So we're going to go to 8,000. We're going to get a word's worth of data, bring it back. And then when we're done, we're going to go in post, edit that register, and increment it to 4. So you can imagine that if you're iterating through loops, right, you want to keep track of where you're pointing at. These are useful tools for loading and storing information and keeping track of those iterations. What questions do we have? 0 questions? Thank you.
So the post-indexing and pre-indexing, you're going to do 2 different things because the order of the way the memory is being updated is different, right?
No.
Well, because for post-indexing, you grab 0 through 3, right? And then after you update it,
yes.
If you have 4, you grab 4 through 7.
Yes. But it's not because of memory. It's because of how the instruction wanted to do. It's just keeping track of, like, imagine you're iterating through a loop when you're adding a value or going through memory or something. And it's just like keeping track of when do you update this variable here. And so now we have hardware to support that because it's such a common task.
Right, but that changes what you're grabbing.
Yes, it does, yes. Okay. So there's a summary. Okay, so for this load instruction, what is the largest possible offset that can be achieved within the immediate? So why don't you take a couple, 30 seconds to chat and come up with an answer. Yes.
Why would you say that?
I hate you guys.
Too many times to not know this number.
All right, what do we think? What's the largest possible offset you can get with an immediate?
1095?
Yep, exactly. Because it's just saying here's the value that could possibly fit in these 12 bits. What's that going to be? 4,009, whatever it is, 4,095. You could do, so this is a load immediate, which is different than a load register. Register can hold the full address. This is just if you're trying to, there's giving you some preference to this lower space, right? That these are the things that you can jump to easily without having to do, put that value into a register first. Okay. Yeah.
Well, I was thinking it might be signed. Why is it not? Why would it not be signed?
There's different encodings. What did I say? What is the largest possible offset? Yes, there are different encodings that can be signed. I did not give that to you, so you could be negative as well. For an immediate though, not for immediate. You can do with offset indexing. You can be negative, but not with an immediate, right? So you can have. Sorry, I misspoke. So this value can be negative. right? Yeah.
Is that value not the immediate 12?
That is the immediate 12. So I don't know how, in this encoding, I don't know how we're going to make it. I think it might have to be a different encoding that would make it negative. But yeah, that would be plus or minus 256 or whatever. Or whatever it would come out to be. Okay, I'll look it up. I'll go figure out what the encoding is for a negative number and how they did this. Notice that I don't think it's signed. 73. Negative coding. Okay. How much can we get through? We're well behind. Let's just do branching and get out of here. We can do that very fast. What do you want to know? So branching is very similar to what you learned in 370. So you're going to branch to a label, right? A label is a place in code. And when you compile in the binary, the floor planner will go replace the label with a memory address. You can branch with the link register. You can branch with the indirect link register, and you can branch indirectly. That's probably not the most exciting part. But you can go and modify all those instructions with conditionals. And where do those conditionals get set? Those conditionals get set in your ALU flags. And so previous instructions, like an add, can set that flag, and then you can do in a conditional. So you could be like branch equal. And so you would just denote that as B equals a label. And if this condition is set, then you get to go and actually execute that branch. And then there's all the possible variants you could imagine off of those ALU flags. There's also, if you want to purposefully set those ALU flags, right, where you don't have an operation, you can say, I want to compare. There's specific instructions for that. So you get compare, compare negative, test equivalents, and then test, where you get to go and test two values to figure out if your ALU flag should be set. All right, and with that, nope, we're going for it. All right, let's try and figure out how to add all this stuff together. Last concept of the class. Here we want to do a simple thing. We just want to iterate x. We're going to add 1 to it. So here is some assembly of how it could get done. So here we're going to load some value at this address into this register. We're going to add 1 and store it back into memory. So we're going to try and unify all this stuff together. Here we have registers in a core. We have memory. Okay? We have code space. We have data space. And then we're not visualized directly is the instructions. So here we have a program counter that's going to go over to some memory location. Here I've decoded this instruction. Let's assume that they're all 32-bit instructions for now. Make our lives easy. We've decoded it into, well, it is load register. That would go into, let's see, we had to fetch that and decode it and everything. Now we're going to go and load this value at that memory location, grab that, and place it here. Okay, so we've gone and loaded the value, the address is stored in R0, and gone out to memory, grab that and place it into R1. Then we're going to, the program counter is going to increment, going to the next instruction that happens to be add R1 to 1, or add 1 to R1. And so here our ALU is going to go 1, and we're going to go increment that. And then our program counter is going to increase by 4. Again, we're just assuming these are 32-bit instructions. We're going to go and get the store command. It's going to say take the value that is in R1 and place it in the address defined by R0. And now we're going to go out to memory, and we're going to go increment that value. Okay? So that's how all those things link together. You got 2 minutes worth of questions. Somebody's got questions. Everybody wants to leave. Thank you.
The negative encoding.
Yep.
There's a T3 encoding for instructions with negative. There's a U bit, and then
That's good that I have smarter students than me. They just solved that right away. Okay, well, I will update and tell the rest of the class later. Thank you for pointing that out. All right, thanks. U-bit. Let's look at that.